Okay, let's unpack this. Welcome back, everyone, to the Urban Herald and the second installment of our series, When the World Broke.
Yeah, it's great to be back.
Our mission, as always, is to dive deep, really deep, into those moments where a single event just, well, ripped the fabric of civilization and sent history spinning in a new direction.
And after exploring the Lisbon earthquake last time, which reshaped Enlightenment thinking, today we're looking at something even bigger in terms of sheer physical scale.
Absolutely. Our focus today is the Mount Tambora eruption in 1815. This wasn't just any eruption, it was the most powerful volcanic explosion in recorded history.
And its global aftermath was so severe, it earned its own chilling name. 1816 became known as the year without a summer.
It's just an incredible case study in cascading system failures, isn't it? We're not just talking about a disaster stuck in, remote Indonesia.
No, not at all. This was a planetary shock, a system shock that literally traveled around the globe, high up in the stratosphere.
And triggered this cascade of effects that seem completely unconnected at first glance. I mean, think about it. A volcano erupts in Indonesia. And it directly inspires Mary Shelley to write Frankenstein in Switzerland.
Right. And it leads to the invention of the bicycle in Germany.
And, maybe most horrifyingly, it kicks off the first truly global cholera pandemic, a pandemic that killed tens of millions over the next century. It's staggering.
It really is. And if we connect this to the bigger picture, what's so fascinating and frankly terrifying about Tambora is how clearly it shows nature's power to disrupt human society on a massive planetary scale, even back then.
So for this deep dive, we've pulled together the research, looked at the sources to really understand the science behind it. How did that blast turn into a global climate crisis?
And we'll definitely explore those ripples, the cultural shifts, the technological innovation born from necessity, the economic chaos. It touched everything.
Our goal is simple, to leave you, our listeners, with a thorough understanding of one of history's most pivotal, yet maybe often overlooked, environmental catastrophes.
Let's start then at the source. Sumbawa Island, Indonesia, before 1815.
Right, before the cataclysm. What was it like? Well, for the people living there, it was a relatively stable world, it seems.
You had Mount Tambora itself, this majestic peak soaring to, about 4,300 meters?
Yeah, huge. One of the tallest in the entire Indonesian archipelago. And for centuries, it was just there, considered dormant.
Supporting life, actually. Its slopes were fertile, volcanic soil, good for agriculture. You had rice terraces, timber.
And thriving communities. Two local kingdoms, the sultanates of Tambora and Pekat, were well established there. Life revolved around the mountain.
But beneath that apparent calm, that stability, there were these immense, relentless geological forces at work. It was deceptive.
Deceptive is the right word. Tambora sits right at a major geological boundary.
Exactly. It's where the Australian tectonic plate meets the Eurasian plate, a classic subduction zone.
So the Australian plate, being denser oceanic crust, is constantly being forced down underneath the Eurasian continental crust.
Right. And that process, subduction, it's not gentle. It drags down water, minerals, and this destabilizes the mantle rock above it, generating huge amounts of magma, molten rock.
And the specific type of magma here is absolutely critical to understanding why Tambora was so violent.
It really is. Because this was a long, slow process, the magma chamber beneath Tambora became incredibly rich in dissolved gases, water vapor, CO2, sulfur dioxide.
And crucially, it was high in silica.
Yes, high silica content.
Right.
That makes the magma extremely thick, viscous. Think of it like sticky honey or molasses.
And because it's so thick, it traps those volcanic gases really efficiently. The pressure just builds and builds and builds.
It can't escape easily, so you're not setting up for a gentle lava flow like you might see in Hawaii. You're priming the system for a catastrophic explosion, a shattering release of pressure.
But the people living there, they had no idea about any of this, scientifically speaking. The warning signs were there, but they went unheeded or maybe misinterpreted.
Well, our sources suggest there were signs. Subtle earthquakes, rumblings in the region starting around 1812.
Locals apparently reported steam vents opening up on the mountainside, fumaroles, releasing sulfurous gases, sometimes killing patches of vegetation.
But without seismometers, without gas monitoring, how would they know? These were just weird events, interpreted through their own myths, their local beliefs, not through geology.
They're living right on top of this ticking time bomb in this intimate relationship with the mountain, but completely unaware of the scale of the danger.
Until April 1815.
Yeah, the beginning of the end. It started actually somewhat subtly on April 5th.
Relatively subtly, yes. The initial explosions began. We now know this was phase 1. but the sound carried for incredible distances.
Heard 1,400 kilometers away, wasn't it? In Batavia, now Jakarta, on Java.
That's right. The military officers there, they heard this deep rumbling sound and genuinely thought it was distant cannon fire, a naval battle happening somewhere out at sea.
They actually sent ships out to investigate this phantom battle.
They did. Shows you the scale of the sound waves even from those initial blasts. But that was just the prelude.
Just clearing its throat, as you said. The real cataclysm, the main event, hit 5 days later, April 10th, 1815, around 7 p.m. local time.
This was the moment of peak violence. A single, truly cataclysmic instant, as one source puts it. The pressure release was so enormous.
Its top third of the mountain just in. Vanished. That majestic 4,300-meter peak disintegrated. Gone.
The sheer scale is hard to grasp. We use the Volcanic Explosivity Index, the VEI scale. Tambora scored a VEI 7.
Which sounds abstract, but let's put it in perspective. Mount St. Helens in 1980. That was a big eruption, VEI 5.
Yeah.
Tambora was 100 times more powerful.
100 times, and even compared to Krakatoa in 1883, which is maybe more famous, Tambora was 10 times larger than Krakatoa.
Mind-boggling numbers. It
Yeah.
threw out something like 100 to 150 cubic kilometers of rock, ash, and gas.
Just think about that volume. And the eruption column, the cloud of material, it reached an altitude of 43 kilometers.
43 kilometers.
It's-
That's well into the stratosphere.
Yeah.
Way above weather systems.
Way above. And the immediate destruction on Sumbawa itself was just absolute, total.
You had pyroclastic flows, these superheated, incredibly fast avalanches of gas, ash, rock.
Moving at speeds maybe up to 200 meters per second. 200 meters per second. Incinerating everything instantly.
And when those flows hit the sea,
They generated tsunamis. Waves maybe up to 4 meters high, washing over nearby islands, adding to the devastation.
those two kingdoms we mentioned, Tambora and Pakat, right at the foot of the mountain.
Obliterated. Just wiped off the map in moments.
The eyewitness accounts from nearby islands are just chilling,
Yeah.
apocalyptic. One observer wrote about the mountain appearing like a body of liquid fire.
Yeah. Extending itself in every direction. The light effect's intense. Brighter than 1,000 lamps. It must have been terrifying beyond imagination.
And the ash, the sheer volume of ash falling from that massive cloud.
Unprecedented. It created total darkness. Hundreds of kilometers away, people reported not being able to see their own hands in front of their faces, even at midday.
Having to light candles in the morning because day had turned into night for almost 2 days straight in some places.
The immediate human cost was horrific. Around 12,000 people killed instantly by the blasts, the flows, the tsunamis.
But that was just the beginning of the death toll, wasn't it?
Tragically, yes. The longer-term impact pushed the total number of deaths to an estimated 71,000 people, mostly from starvation and disease in the following weeks and months.
Because the ashfall completely destroyed agriculture on Sumbawa and nearby Lombok and Flores, choked water sources. There was nothing left.
And beyond the human lives, there was another profound loss: the entire culture of the Tambora people, their language, their traditions, their history, all erased. A complete cultural extinction event in a matter of hours.
Just gone. It's hard to comprehend.
And the physical evidence lingered for months. Ships hundreds of kilometers away reported sailing through massive rafts of fluting pumice stone, sometimes meters thick, clogging the sea lanes.
A scene of utter chaos and breakdown. But as you said, the real global catastrophe, the one that earned 1816 its name, was only just beginning, silently and visibly high above the clouds.
Exactly. That's the pivot point.
So, okay, we've got this immense localized disaster. Thousands dead, an island devastated. But how? How does that event in, let's be honest, a pretty remote part of the Dutch East Indies, how does that lead to farmers losing their crops in Massachusetts? Why did it snow in England in the middle of July the next year? That's the puzzle.
And the answer lies in the chemistry and the physics of the atmosphere. It's about what Tambora threw up, not just out.
It wasn't just ash and rock.
No. The key was the massive injection of volcanic gases, specifically sulfur dioxide, SO2, and critically getting it high into the stratosphere.
How much SO2 are we talking about?
Estimates suggest around 60 megatons. 50 million tons of SO2, just a staggering quantity. To compare, the 1991 Mount Pinatubo eruption, which did cause noticeable global cooling for a year or two.
Right, I remember that.
Pinatubo released maybe 10 megatons of SO2. Tambora released 6 times more.
6 times, okay. And why is the SO2 so much more important for the global climate than the ash? Most people picture ash clouds blocking the sun.
And ash does block the sun initially, but ash particles are relatively heavy. They fall out of the atmosphere quite quickly, days, maybe weeks. Their impact is mostly regional, causing darkness like we described.
But the SO2 behaves differently.
Very differently. Once that SO2 gas gets pushed up into the stratosphere, that 43-kilometer high column was crucial. It undergoes a chemical transformation.
Okay, what happens?
It reacts with water vapor up there and other atmospheric chemicals, and it forms tiny microscopic droplets of sulfuric acid. These are called sulfate aerosols.
Aerosols.
Mhm.
Tiny droplets, not solid ash particles.
Exactly. And because they are microscopic, they are incredibly light. They don't fall out quickly. They stay suspended up there for a very long time.
Why do they stay up so long in the stratosphere specifically?
Because the stratosphere is very different from the lower atmosphere, the troposphere, where weather happens. The stratosphere is dry, it's stable, there's very little vertical mixing.
And critically, no rain.
No rain, no snow. There's no precipitation up there to wash these aerosols out, like what happens with pollutants lower down. So these sulfate aerosols can remain suspended for years.
How long are we talking?
Typically 2 to 3 years, sometimes even longer. And while they're up there, they form this vast, thin, almost invisible veil spread across the globe.
A veil that acts like a layer of sunscreen for the entire planet.
That's a perfect analogy, a planetary sunscreen. Because these tiny droplets are incredibly effective at scattering incoming sunlight, reflecting a portion of it back into space before it can reach and warm the Earth's surface.
And that is the mechanism for the volcanic winter, the sustained global cooling.
Precisely. The data shows a global average temperature drop of somewhere between 0.4 and 0.7 degrees Celsius.
Which might not sound like a huge number on its own.
It doesn't, but global averages mask much larger regional variations. And critically, the cooling effect is amplified over land, and particularly at higher latitudes.
So places like Europe and North America got hit much harder.
Much harder. Land temperatures in some of those regions dropped by as much as 3 degrees Celsius below normal during the crucial summer growing season of 1816. 3 degrees. That's massive.
The cooling effect, the reflecting of sunlight, that's what scientists call climate forcing, right?
Yes. The aerosols forced a change in the planet's energy balance. And the distribution wasn't even. Stratospheric winds, which generally flow eastward and towards the poles.
Carry this aerosol cloud predominantly over the Northern Hemisphere.
Correct. Which explains why Europe and North America experienced the most dramatic and, well, agriculturally devastating impacts. The year without a summer was primarily a Northern Hemisphere phenomenon.
And it wasn't just cooling. That might have been bad enough, but it messed with the weather patterns in other ways too, didn't it?
Oh, absolutely. Disrupting the temperature balance like that completely destabilized established atmospheric circulation patterns. It wasn't just colder. The weather became chaotic, unpredictable.
How so?
In some areas, it led to severe drought, possibly because the cooler surface reduced evaporation, or maybe it shifted the jet streams. But in other areas, it caused the opposite. Unprecedented, relentless rain and flooding. Huge low-pressure systems seemed to just stall for weeks on end.
And you mentioned earlier the impact on Asia.
Yes, perhaps the most catastrophic disruption affecting the largest number of people was the significant weakening of the Asian monsoon.
Right, the monsoon, which is absolutely vital for agriculture, especially rice, feeding billions of people. How could aerosols high up in the stratosphere affect surface winds like the monsoon?
It comes back to temperature differences. The monsoon is driven fundamentally by the land mass of Asia heating up much faster than the surrounding oceans in summer. This creates a large, low-pressure zone over land that pulls in moist air from the sea, bringing the rains.
Okay.
But the Tambora aerosols, acting as that sunscreen, reduced the amount of sunlight reaching the Eurasian landmass. It didn't heat up as much or as quickly.
So the temperature difference between land and sea was reduced.
Exactly. The thermal contrast weakened, and that weakened the whole engine driving the monsoon circulation.
And this happened for how long?
The sources indicate the monsoon was significantly weakened for 2 consecutive years, 1816 and 1817. This led to widespread drought, crop failures, and famine across India, China, and Southeast Asia, adding millions more to the global tally of victims, far from the direct volcanic impact zone.
It's just chilling to realize the global interconnectedness of the climate system even then. And this event, Tambora, it's become a crucial natural experiment for scientists today, hasn't it?
Absolutely invaluable. We have historical records, geological evidence, and now, crucially, ice core data.
Ice cores? From where?
From Greenland and Antarctica. By drilling deep into the ice sheets, scientists can analyze layers of ancient snowfall. And trapped in the ice from 1816, 1817, 1818, they find a distinct spike in sulfate concentration.
Ah, direct physical evidence of those stratospheric aerosols falling out eventually.
Precisely. It confirms the chemistry, confirms the timescale. The data shows elevated sulfates for nearly 5 years after the eruption, validating that long atmospheric residence time.
And this data helps test modern climate models.
Enormously. It allows scientists to check if their models can accurately simulate the climate's response to a sudden, massive injection of aerosols, a huge solar dimming event. It's a key benchmark.
And it also informs discussions about, well, deliberately messing with the atmosphere, geoengineering.
It does. The main proposed method of solar radiation management involves artificially injecting sulfate aerosols into the stratosphere to counteract global warming. Tambora provides our best, perhaps only, large-scale case study of what the real-world consequences and potential side effects of doing that might be. It's a cautionary tale written in the climate record.
Okay, let's bring this back down to the human level. Let's go to Europe and North America in 1816, the year without a summer. What was it actually like?
It wasn't just a cool summer. It was, for Europe certainly, the coldest summer in the entire instrumental record, stretching from the mid-18th century right up to the year 2000. The weather wasn't just unpleasant, it was actively hostile to life, especially agriculture.
We have some unbelievable meteorological facts from that year.
We do. Snowfall. In the English Midlands. In mid-May. Killing young crops.
And July 1816 still holds the record as the coldest July ever recorded in England.
The overall result across much of Europe and northeastern North America was a catastrophically short growing season. In Central Europe, many areas had fewer than 200 frost-free days. Normally, you need closer to 290 for greens like wheat to mature properly.
The outcome was inevitable then, a massive, widespread agricultural collapse. This wasn't just a bad harvest, it was a systemic failure.
Leading directly to what historians call the last great subsistence crisis in the Western world. Crops failed everywhere. Persistent frosts nipped buds, endless cloud cover reduced sunlight for photosynthesis, and in many places, relentless cold rain waterlogged the fields, rotting seeds and roots.
You mentioned Switzerland earlier, with the grapes.
Yeah, a vivid example. Switzerland relies heavily on its vineyards. The cold and lack of sun delayed the grape harvest until early November. And even then, the grapes were reportedly still hard, green, completely unripe, useless for wine.
And staple grains, wheat, oats, barley.
Production plummeted, down 50%, even 80% in parts of Germany, France, Switzerland, Poland. People faced starvation.
Ireland seems to have suffered particularly badly in Western Europe.
It did. Ireland endured about 8 solid weeks of cold, continuous rain right when the potato crop, their staple food, should have been maturing. The crop was wiped out. Total failure.
Leading directly to famine.
Famine and then disease. Typhus fever spread rapidly through the weakened, malnourished population. It was a devastating blow, especially as the country was so dependent on the potato.
And this put farmers everywhere in just an impossible position.
An absolutely brutal dilemma. Your harvest has failed, you have meager reserves. Do you eat the seed grain you've saved just to survive the coming winter?
Knowing that means you'll have nothing to plant next spring.
Exactly. Or do you gamble? Do you starve yourself further, hoping against hope that if you plant the seed, next year will be better? It's a choice between immediate survival and any hope for the future. Many were forced to eat the seed stock.
Which, of course, prolongs the crisis into the following years, even if the weather improves.
It guarantees it. The agricultural recovery was severely hampered for years because of that loss of seed and also breeding livestock.
And this misery wasn't confined to the countryside. It rapidly spread to the cities.
Oh, yes. Urban populations were entirely dependent on food coming in from the countryside. As supplies dwindled, food prices spiked dramatically.
How bad did it get?
Bread prices tripled, even quadrupled in many major European cities. London, Paris, cities across Germany. This shattered the fragile social contract, the sort of moral economy where people expected basic necessities to be accessible.
No, and people are starving and desperate.
You get unrest. This period saw widespread food riots across Europe. France, Germany, Switzerland, even England saw disturbances. Crowds attacked grain convoys, looted bakeries and granaries. Governments were terrified of revolution.
It really exposed how fragile those early 19th century societies were, especially coming right after the Napoleonic Wars, which had already exhausted resources and disrupted trade.
Absolutely. Government responses were often slow, fragmented, inadequate. They simply didn't have the mechanisms or often the reserves to cope with a crisis of this magnitude.
The economic shockwaves went beyond just food prices, right? You mentioned livestock.
Yes, the livestock sector was hit incredibly hard. It's a cascading effect. Grain prices soared, hay was scarce and expensive due to the failed harvests. Farmers simply couldn't afford to feed their animals through the winter of 1816-17.
So they had to.
Mass slaughters, horses, cattle, sheep, pigs were killed off in huge numbers across the continent that autumn and winter.
Which must have temporarily crashed meat prices.
It did, briefly, a sort of morbid glut of cheap meat on the market for a few months. But the long-term consequence was devastating. It decimated breeding stocks.
Fewer animals to pull plows, less manure for fertilizer, fewer animals giving milk or wool.
Exactly. The shortage of draft animals, horses, and oxen crippled planting efforts in 1817 and 1818. The lack of dairy cattle, prolonged food shortages, it took years for herds to recover, extending the misery and reliance on expensive imports.
It's just a stark reminder, isn't it? How quickly things can fall apart when the basic systems we rely on, food, weather, are disrupted on such a scale. The veneer of civilization feels very thin sometimes.
It really does. But amidst all this darkness, this gloom and suffering and social collapse, something quite extraordinary happened. Creativity flourished.
The paradox. Out of the darkness came these cultural masterpieces. It seems the very weirdness of the atmospheric conditions, the sense of confinement, maybe even the apocalyptic mood, fueled artistic creation.
And the most famous example has to be what happened at the Villa Diodati by Lake Geneva in Switzerland.
Right, the summer of 1816, you have this group of young English writers and intellectuals. 18-year-old Mary Godwin, who would soon be Mary Shelley.
Her partner, the poet Percy Shelley, the flamboyant Lord Byron, and Byron's physician, John Polidori.
They'd gone to Switzerland hoping for sunshine, boating, alpine scenery.
And instead, they got what Mary Shelley later called a wet, ungenial summer. Relentless, cold, fog, incessant rain that often confined us for days to the house, weather directly caused by Tambora's aerosols.
Stuck indoors, bored, surrounded by this gloomy, unnatural weather.
Byron famously proposed a challenge. We will each write a ghost story.
And this is where Frankenstein comes from.
Directly. Mary Shelley had been listening intently to conversations between Byron and Shelley about the latest scientific ideas, particularly galvanism.
The experiments using electricity to make dead muscles twitch. Spooky stuff.
Very spooky. The idea that maybe electricity held the secret to life itself. And one night, June 16th, 1816, after these discussions, Mary had what she called a waking dream.
She envisioned it.
She saw the pale student of unhallowed arts kneeling beside the hideous thing he had put together, the creature stirring, coming to life.
Wow. And from that dream, born in that volcanic gloom, came Frankenstein, the modern Prometheus.
A novel that explored huge themes, scientific ambition, playing God, the consequences of uncontrolled creation. Themes that resonated incredibly powerfully against the real-world backdrop of uncontrolled natural forces causing chaos and suffering. That anxiety about human hubris felt very real in 1816.
And Byron himself wasn't idle during that gloomy summer.
No, he channeled the atmosphere directly into his poem Darkness, written right there in July 1816.
The opening line says it all. I had a dream, which was not all a dream. The bright sun was extinguished.
It's pure apocalypse. He was clearly drawing on reports of the celebrated dark day, times when the sky was so dim from the aerosols that birds went to roost at noon, people needed candles inside. His poem reflects that fear of total societal collapse, the famine, the desperation that was actually happening across Europe.
And we shouldn't forget Polidori, the physician. His contribution to that ghost story competition was The Vampire.
Right. Maybe overshadowed now by Dracula, but Polidori's story was hugely influential. It basically created the template for the aristocratic, sophisticated, yet deeply predatory vampire that dominated literature afterwards. Another monster born from the Tambora summer.
The cultural impact even stretched into painting, didn't it? With J.M.W. Turner.
Yes, this is fascinating. Turner, the great English landscape painter, master of light and atmosphere. He was, completely unknowingly, documenting the Tambora aerosols in his work.
How so? His thing, The Sunsets.
Exactly. His paintings from the years immediately following Tambora, say 1816 to 1818, are famous for their incredibly vivid, dramatic, often fiery red and orange sunsets and sunrises.
Why did the aerosols cause that?
It's physics. Those tiny sulfuric acid droplets high in the stratosphere are very good at scattering the shorter wavelengths of sunlight, the blues and greens. This is called me-scattering.
So the blue light gets scattered away.
Leaving the longer wavelengths, the reds, the oranges, the yellows, to travel straight through to our eyes, especially when the sun is low on the horizon. It creates those spectacular, almost unnaturally intense colors.
Turner's just painting what he saw.
He was painting the atmospheric effect of the volcanic veil. And what's amazing is the scientific correlation that researchers have found much more recently.
What did they find?
By analyzing the pigments in Turner's paintings, specifically the ratio of red to green he used in his sunsets from that period, they found it correlates remarkably well with the actual amount of volcanic aerosols measured in the Greenland ice cores for those exact years.
No way. So his art serves as a kind of proxy record of atmospheric pollution.
Precisely. Great art became an accidental but quantifiable source of scientific information about past atmospheric conditions. It's an incredible intersection.
Amazing. Okay, let's shift gears again. From culture back to more tangible impacts. Innovation driven by crisis. And, tragically, global disease.
Yes, the long tail of Tambora is profound. Let's start with innovation, specifically in transport.
Because the year without a summer didn't just kill crops, it killed horses.
En masse. We touched on this. The soaring price of oats and hay made feeding horses impossible for many. Widespread starvation plus deliberate culling meant hundreds of thousands of horses died across Europe.
And horses were the engine of the 19th century economy. Transport, agriculture, military.
Everything relied on horsepower, literally. Their loss created a massive acute transportation crisis. Goods couldn't move, mail systems faltered, personal travel became incredibly difficult and expensive. There was an urgent need for an alternative.
Enter Baron Karl Drais in Germany.
Yes, Baron von Drais was an inventor, a forestry official, and he saw firsthand the devastation caused by the horse crisis in his region. He set out to create a mechanical alternative, a human-powered vehicle.
And he succeeded. On June 12, 1817, just 2 years after the eruption, right in the midst of the ongoing food shortages, he made the first documented journey on his invention.
His Laufmaschine, meaning running machine. We know it better as the Draisine or sometimes the dandy horse.
Describe it. What did it look like?
Very simple, really. 2 wheels in line, a wooden frame, handlebars for steering. But crucially, no pedals.
No pedals. So how did you move?
You pushed off the ground with your feet, like a kid's balance bike today. You'd sort of run or glide along. It looks awkward now, but it was revolutionary then.
And the bicycle invention, or its earliest ancestor, was born directly out of this volcanic crisis.
Absolutely. It was driven by pure economic necessity. Think about the cost comparison. A horse, before the crisis, might cost the equivalent of, say, 1,900 pounds in today's money. Drace's Laufmaschine cost about 20 pounds.
Plus, no feeding, no stables, no vet bills.
Exactly. It was a direct response to the failure of the animal-based transport system. It's one of the clearest examples in history of a major environmental disaster forcing technological innovation that had huge long-term consequences. The dandy horse is the direct ancestor of every bicycle and motorcycle on Earth.
Incredible. But while that was an innovation, albeit born from suffering, there was a far darker, deadlier consequence linked to Tambora's climate disruption.
Yes, the cholera connection. This is perhaps the most devastating and scientifically fascinating long-term legacy.
I still struggle to connect the dots here. Volcano in Indonesia, pandemic starting in India years later. How?
It comes back once again to the disruption of the Asian monsoon. Remember, Tambora's aerosols weakened the monsoon for 2 straight years.
Right, causing drought and crop failure.
Yes, but it wasn't just drought. That weakening also led to unseasonal patterns, periods of intense drought, followed by unusually heavy, concentrated rainfall and flooding, particularly in the Ganges Delta region of the Bay of Bengal.
And the Bay of Bengal is the homeland of the cholera bacterium.
It's the natural reservoir for Vibrio cholerae, and this drastic environmental change, the cycle of drought-concentrating bacteria, followed by massive floods spreading it through contaminated water sources, seems to have created the perfect conditions for the bacterium to evolve.
Mutate.
To mutate into a new, far more virulent strain. A pandemic strain that the local population had no immunity to.
And this new strain emerged when?
It appeared suddenly and explosively in Bengal in 1817, just ripping through communities. It killed, estimates suggest, 10,000 British soldiers stationed in India within weeks, giving us some of the first detailed records.
And from India, it spread?
It spread rapidly along the newly expanding British trade and military routes. This was the dawn of globalization, in a way. Cholera hitched a ride.
creating the first global pandemic of cholera.
The first of 7 major cholera pandemics that would sweep the globe during the 19th century. It reached the Middle East, Russia, then Western Europe by about 1830, and crossed the Atlantic to the United States by 1832.
The long-term impact is almost unimaginable.
Tens of millions dead worldwide over the century. Cholera utterly transformed urban life and public health. Fear of cholera finally forced governments to invest in massive sanitation projects, clean water supplies, sewage systems. It drove the development of modern epidemiology, with figures like Dr. John Snow in London painstakingly tracing outbreaks to contaminated water pumps. All of this spurred by a chain reaction starting with Tambora.
The environmental consequences, the cultural impact, the technological change, the pandemic. What about the purely financial fallout? The economic shockwaves must have been immense, too.
Oh, absolutely. Tambora triggered what was arguably the first truly global, synchronized economic crisis of the modern era.
We talked about the food price spikes. Remind us of the scale.
Just staggering. Grain prices in Europe jumped 300, even 400% almost immediately. In the U.S., particularly New England, which was hit hard by the cold summer, things like oatmeal apparently soared by nearly 800%.
That reflects total scarcity, but also hoarding, speculation, the breakdown of transport.
All of it. Intense financial chaos. And that pressure lasted for several years until European agriculture slowly began to recover around 1818, 1819.
But the recovery itself caused another problem.
Yes, a different kind of crisis. As harvests improved and food flooded back onto the market, prices collapsed. This sudden deflation burst a speculative bubble that had built up, particularly in the United States.
Leading to the Panic of 1819.
Exactly. The first major, sustained financial depression in U.S. history. Banks had lent irresponsibly, especially for land speculation on the frontier, assuming high commodity prices would continue. When prices crashed, loans couldn't be repaid, banks failed, businesses went bankrupt.
Thomas Jefferson called it a time of unparalleled distress.
He did. The pain was widespread, from farmers losing their land to merchants facing ruin. And this panic had a profound effect on American society.
A major societal shift.
Yes. It significantly accelerated westward migration. Families in New England, ruined by the crop failures and then the financial panic, had little choice but to seek new opportunities further west.
So Tambora indirectly fueled the westward expansion of the U.S.
It provided a major push. This wave of migration created demand for and labor to build new infrastructure to connect the expanding West with the East. Think of the Erie Canal, which gained huge momentum during this period, partly to transport Western grain back to Eastern markets more cheaply. Tambora's legacy is literally etched into the map and economy of the United States.
Which brings us, inevitably, to the present day. This all happened 2 centuries ago. What does it teach us now? What are the vulnerabilities today?
It's a crucial question. The core lesson, I think, is about interconnectedness and resilience. The 19th century world was vulnerable because of poor communication, limited science, weak infrastructure.
But our world, our modern systems, are hyper-connected, optimized for efficiency. Does that make us safer or more vulnerable in different ways?
That's the paradox. In some ways, potentially more vulnerable. Our efficiency might be our Achilles heel in the face of a Tambora-scale event.
How so? Take food systems.
Our global food system relies heavily on just-in-time supply chains and vast agricultural monocultures, huge regions growing single, high-yield varieties of wheat, corn, rice, optimized for current conditions.
But with very little diversity or buffer.
Exactly. A volcanic winter lasting 2 or 3 years with significant cooling and disrupted rainfall. It could devastate these specialized monocultures globally, simultaneously. We lack the widespread use of diverse, locally adapted crops and the large strategic grain reserves that societies use to maintain. Efficiency has often trumped resilience.
And transportation. We saw what a relatively small Icelandic eruption, Age of Geological in 2010, did to air travel.
Right. That was a VEI-4. It shut down European airspace for 6 days, cost billions. A VEI-7, like Tambora, it wouldn't be days, it could be months, potentially years of severe disruption to air travel worldwide from ash and corrosive aerosols. Global trade, tourism, supply chains crippled.
And we have technological vulnerabilities they didn't have in 1860.
Completely new ones. Think about our reliance on satellites.
GPS, communications, weather forecasting.
All potentially threatened. The sulfuric acid aerosols could directly damage sensitive satellite components through corrosion, and the atmospheric changes could increase orbital drag, degrading orbits faster. Imagine losing reliable GPS globally. It affects shipping, aviation, finance, precision agriculture, emergency services, everything.
The potential for cascading failures across multiple critical systems seems much higher today.
It probably is. Our interconnectedness makes us efficient, but also potentially brittle if a key node fails.
So if another VEI-7 eruption is, geologically speaking, inevitable at some point, what can we do? How do we build resilience?
We can't stop the eruption, but we can prepare for the consequences. The sources point towards prioritizing redundancy and diversity, perhaps pulling back slightly from pure efficiency.
In agriculture, that means.
Investing seriously in developing and promoting volcanic winter crops. Things that can tolerate lower light levels, cooler temperatures, root vegetables, certain hardy grains, maybe even researching indoor or alternative food production methods, diversifying away from the big monocultures.
And rethinking supply chains, moving away from purely just-in-time.
Yes. Rebuilding strategic stockpiles, food, medical supplies, fuel, critical spare parts. It costs money to store things, which is why we moved away from it, but it buys resilience.
What about infrastructure?
Hardening critical infrastructure, power grids, communication networks against potential atmospheric threats like corrosion or electromagnetic effects. And crucially, since this would be a global crisis, we need robust international cooperation, plans in place before it happens for sharing resources, coordinating responses, managing migration, something sorely lacking in 1816.
It really comes down to valuing long-term resilience over short-term optimization.
That seems to be the core lesson from Tambora.
So wrapping this up, the Tambora eruption stands as this incredibly powerful, almost visceral reminder of nature's capacity to just completely disrupt human systems on a planetary scale.
Absolutely. But it's also a testament to human resilience, adaptation, and even creativity emerging from the darkest times. That paradox is central to the story.
Catastrophe and creativity, famine and Frankenstein, transportation crisis, and the bicycle. They're inextricably linked.
The same forces, ultimately. And the mountain itself still bears the scar. That colossal peak, once over 4,300 meters high, now stands at just 2,850 meters.
With a massive caldera 6 kilometers wide at its summit. A permanent physical monument to the event's power.
It really is, which I think raises an important question for all of us, for you listening.
Go on.
The legacy of 1816, the year without a summer, is complex. We can't control these immense geological forces, but we can control how we prepare, how we respond, how we build our societies.
And our modern society is, in many ways, more complex, more interconnected, maybe more fragile than the world of 1816.
But we also have advantages they didn't. Incredible monitoring technology, sophisticated climate models, near-instant global communication. We should be better prepared.
So here's the final thought, the provocative question for you to take away. We know from the geological record that huge eruptions, like Tambora, VEI-7 events, happen roughly every 500 to 700 years. It's not if, but when the next one occurs, or indeed when the next major planetary scale environmental shock hits, whatever its origin, volcanic, climatic, something else.
Will it be our global system's relentless pursuit of efficiency that defines our experience? Or will it be our capacity for foresight, for building in redundancy, for flexible adaptation, for global cooperation?
Which path will determine our survival, or at least the severity of the disruption? The choice, ultimately, of how much resilience we build into our world, that choice is ours.